I have 9 a.m. Eastern time on my clock. So I think we can start. So welcome everybody to the third day of the Quasars and Galaxies Through Cosmic Time conference. So over the past 2 days, we've had some great talks and great discussions. So I just want to thank again all of the speakers and all of the discussion moderators. There's been a lot of discussion as well going on through the Slack. So if you're not connected through the Slack, you should definitely use it. And that's, I think, it. I don't think we have any other information to give you today. So we can just start immediately with the session. So I'll leave the moderator of this session, Ricardo De Marco. So please go ahead, Ricardo.
Thank you very much, Roberto. Good morning, good afternoon, good evening, everyone. We're going to start this first session of the third day of this conference. I would like just to remind everyone a little bit the time slot given for the invited talk. We have a 30 minutes presentation followed by a 10-minute slot for questions. I will give a warning at 5 minutes before the end of the 30 minutes, and then hopefully I don't have to do that, but 30 seconds before the 30 minutes. And for the contributed talks, there are 8 minutes for the presentation plus 3 minutes for, 8 minutes for the presentation plus 2 minutes for questions, right? And I will give a warning at the 3 minutes before the end of the 8 minutes. Just if you have questions, you can raise your hands or use the Q&A, or also leave your questions on the Slack channel for this session, and you can obviously follow up the discussion there. So I'm going to start with the first talk today. It's an invited talk by Cristina Garcia-Vergara, who will be talking about the obscured and unobscured environment of high Z quasars. Cristina, go ahead.
Yeah, thank you. Okay. Okay, thank you. I'm Cristina Garcia. I'm a postdoc at Lyman Observatory. And first of all, I would like to thank the organizer for inviting me to this great conference. And today I'm going to talk about the environment of high redshift quasars. I'm going to focus on both the obscure and unobscure population of galaxies around the quasars. And first, I'm going to try to give you a general overview about what results we have so far and what are the main complications that we are facing about this topic. And then in the second part of my talk, I'm going to focus on some recent results about systematic search of obscure and unobscure galaxies around a large sample of quasars at redshift 4. So let's start first with a motivation about why we are interested in studying quasar environments in the first place. So first, from a theoretical point of view, the most massive galaxies in the early universe are placed in the most massive dark matter halos, tracing the most massive structures. This is a result and a prediction that is in agreement with most of the n-body simulations and theoretical works. Some works have been trying to also include some evolution of quasar in a cosmological context, and the typical or the generic prediction from these works is that high redshift quasars should reside in massive halos with halo masses greater than 10 to the 12 solar masses over H. Considering this, then the generical theoretical prediction is that quasars should be surrounded by a large number of galaxies. Now, observationally, is much more challenging to make progress in this area because we are talking about the high redshift universe, which is always challenging. However, we first need to know that dark matter halo mass can be directly related to the clustering of a population. That is a result from theoretical studies. And then based on this, we will expect that if quasar trace massive dark matter halos, the autocorrelation function of quasars should be very strong. Unfortunately, we have enough observations so far to measure the autocorrelation of quasars as a function of redshift, and this is exactly what I'm showing here in the plot. This is the correlation length as a function of redshift for quasars, and you can see that at low redshift and until redshift 2, the clustering of quasars is relatively flat, rising a little bit. But from redshift 2 to redshift 4, the clustering dramatically increased. Particularly at redshift 4, Shen et al. 2007 measured a very, very strong quasar autocorrelation function, predicting halo masses about 10 to the 12 solar masses over age, which is also consistent with the theoretical prediction that I mentioned before. So in my opinion, this is the strongest observational evidence that we have so far to think that quasar trace massive dark matter halos. Also, based on this result, the expectation is that we should detect a large overdensities of galaxies around the quasars. And now, until the end of my talk, when I say high redshift, I will mean redshift similar or greater than 4. Then this result has also motivated people to actually detect such large overdensities of galaxies around the quasar. So this is like a different way to observational constrain the quasar's environments. So the usual method to characterize the density field around high redshift quasar is a very simple method. So people target quasar field and they count galaxies around the quasars over a certain volume, which is parameterized by the projected distance from the quasar and the redshift windows that the survey is targeting. And this is the quantity QG is called in this talk at least, is compared with the number of galaxies that you expect to observe in blank fields over the same volume, the quantity QR, or also it's called background number density. So this quantity QR can be measured directly from the observations. If people can target large areas over the sky, can measure QR directly from the observations, but that is not always the case because it's very expensive to do. So the other option is that you can use the luminosity function of the galaxy in question at the redshift in which you are making the measurement. So the overdensity is defined as QG over QR, and people typically claim an overdensity of galaxies around quasar if this quantity is larger than 1. So following this simple approach, most of the work has been done at optical wavelengths, and around 30 quasar fields have been studied so far with this purpose in the last 15 years. So these works target typically Lyman-break galaxies or Lyman-alpha emitters around the quasars. And as you can see here in this plot, in which I'm summarizing the result of all this work in this area, half of the fields show overdensities of galaxies, and the other half show a number density consistent with the background number density. So you can see that there is not consensus at all, at least at optical wavelengths, and there is not clear evidence that quasars are tracing massive dark matter halos as their clustering suggests. However, in the past 3 or 4 years, there has been some serendipitous detection of dusty close companion around high redshift quasars detected with ALMA. So all the works that I'm summarizing in these tables are, well, almost all of them are focused on target the quasar itself and study the host properties, the host galaxy properties of the quasar itself. So the detection of the companion around is just a serendipitous detection. Those are not studies designed specifically to detect fainter galaxies around the quasar. But even though this work claims a very huge overdensity of dusty galaxies around the quasar, between 3 and 60 for the overdensity. And I would like to highlight this work from Roberto De Carli in 2017, who studied 27 quasar at redshift greater than 6, and they found 4 C+ emitters. They here show the cumulative number of companions as a function of the projected distances. And you can see that their measurements are way higher than the background number density, which are shown in these 2 lines. These are the only 2 studies constraining the background number density at that time. And the overdensity that they detect is also interestingly consistent with the clustering of Lyman-alpha galaxies around quasars at redshift 4. So these studies are great, and the results are very exciting. This suggests that dusty galaxy may be strongly clustered around the quasar, but a systematic search for such a population of dusty galaxies is still missed. And we don't have a statistical constraint in this area at these wavelengths, at least. Also, some people have been working on tracing the submillimeter continuum sources around the quasar. The advantage here is that the number count in blank field it's better constrained, but the disadvantage is that we cannot know the redshift of the sources. Here I'm showing first work from Pretty et al. 28, who used SCUBA to study 3 quasar redshift greater than 5. And you can see that they claim an overdensity by a factor of 4 over the blank field expectation, which is the line here. But on the other hand, we also have this more recent work from Champagne et al. 2018, who used ALMA to study a much larger quasar sample at high redshift. And they don't detect any overdensity of dusty galaxy, as you can see here in the black point, which are consistent with the blank field measurements, which is shown here in different color from different studies. However, we need to keep in mind that the overdensity signal of continuum sublimiter sources can be strongly diluted because of the large volume that those sources prove. I'm going to be back to that point later. So now I would like to mention some possible reasons about why these results in general are contradictory, specifically for optical wavelength. So there are several reasons that could be affecting the result. First, we have the issue that almost all the works that have been mentioned so far are targeting individual quasar fields. And then the large statistical fluctuation expected from cosmic variance will explain why they have been inconclusive. So we have a problem with cosmic variance and low statistics. And generally speaking, I would say that targeting about 10 to 20 fields is required to really tackle this cosmic variant issue. This is something that some simulations suggest, and also some observations have been showing this, and I will show a little bit more about that later too. A second complication is that the different works are tracing different volumes. And this is a complication because the overdensity signal may be diluted in different ways. So let me explain better this point. If we expect that galaxies are clustered around the central quasar, then we expect that a power law profile in 3 dimensions, right, from the quasar. So here I'm showing, for example, the overdensity over the projected distance from the quasar. So I'm just assuming a certain delta C, and you're projecting the information over that delta C. So you basically expect high overdensity at small radius and small overdensity at large radius. That is the general expectation. So if, for example, you observe the quasar field with an instrument with a small field of view, you are basically integrating the signal, the overdensity signal over this radial distance. You're going to measure this overall overdensity, which is relatively high. But if you target the same quasar field with an instrument with a much larger field of view, you are integrating over much larger volumes, then your measured overall overdensity will be much lower. So this is a problem because you're diluting the signal, and different works have different instruments. So it's really complicated to compare different studies. And this issue also happened in redshift space. So the argument is exactly the same for a fixed field of view. If you are tracing a larger redshift window, your signal will be much more diluted. And this is actually a very important in the case of, for example, Lyman-alpha galaxy, which cover a very wide redshift range, and even more for sub-millimeter galaxies, because the flux of sub-millimeter galaxies is roughly constant over a redshift between 1 and 7. Then you basically cannot distinguish between foreground and background sources, and you dilute a lot the overdensity. Yeah, a third complication that I would like to mention is systematic errors in the background number density. As I mentioned, the QR is a very important quantity because this need to be accurate to quantify the overdensity. So this usually requires a well-constrained luminosity function, which at optical wavelengths, I would say it's very well measured today for almost all the redshift. That was not the case 15 years ago when all this work in this area started, but today it's very well measured. That is not really the case for sub-millimeter wavelengths, where we just started to have some luminosity function available like 2 or 3 years ago. Here, for example, there's a very nice work from the aspect survey from the GALAXIES 2019, who constrained the luminosity function of CO emitters at redshift between 1 and 4. So this is really the first constraint for CO emissions. And we also have this C+ luminosity function from Alpine survey covering between redshift 4 and 6. So this is just published last year. So we just are starting to get some luminosity function information, which is very critical to characterize the environment of quasars. And the last reason that I want to mention here is that some physical properties could be affecting the galaxy visibility. So in other words, galaxies should be there, but we cannot see them when we only detect them at optical wavelengths, for example. So to just give some example, the ionizing radiation from the quasar, for example, may both increase or decrease star formation in close galaxies. This is an opposite of effect that is really hard to disentangle, but this could affect the Lyman-alpha galaxy, Lyman-alpha emitters, for example, that we see in the environment of quasars. I think Tommaso is gonna talk more about this topic in the talk just after this one. And other example is, for example, galaxies in quasars environment could have different properties than galaxies in blank fields, just because of the presence of the quasar or because they are in dense environment and the evolution of galaxies maybe is different. So we can have galaxies more with higher or lower star formation efficiency and star formation rates with more or less dust, etc. So the only way to really trace the whole population of galaxies around quasar is by looking at different wavelengths. In particular, optical and sub-millimeter wavelengths provide a very nice or a more complete picture. Now that I have been mentioned this complication, I would like to move and show you what other approaches we can use in the coming years to try to solve some of these complications. So one powerful method to characterize the density field around high redshift quasar is actually the cross correlation function. So instead of just focusing on measure the individual overdensities in individual quasar fields, we can target a larger sample of quasars and constrain the quasar galaxy cross correlation function. This is defined by this equation here, which is the correlation function in 3D, but is integrated over the volume. The estimator that we usually use is QR over QG over QR -1. So this is basically the overdensity -1. And the difference with before is that in this case, we of course have more statistics because we are targeting more sources, more quasars. So we can really trace the overdensity in rings from the quasar and recover this power law shape that is expected to be observed. And the advantages of this is, of course, this overcome has high cosmic variance because you're looking at different locations in the universe and increase the number statistic. It also reveals the exact profile of the overdensity, and it also allows us to fit R0 and infer halo masses for the different populations. Then the expectation is that if galaxies are accumulated around the quasar, then this will imply a very large quasar-galaxy cross-correlation function. This technique has been actually very widely used at lower redshift, a redshift lower than 3, and mostly at optical wavelengths, but there is not much work at higher redshift and not at different wavelengths. So in the rest of the talk today, I'm gonna show you the results of a systematic search of obscure and unobscured galaxies that we have been working on with our group in the past years. Okay, so we performed a survey of Lyman-alpha emitters and CO emitters in the environment of 17 quasars at redshift 4. Here I'm showing one example of the optical imaging of one of our fields. We use VLT to observe them like 1 hour per target or less in order to look for Lyman-alpha emitters. On the other hand, I'm showing the one example of our ALMA data that we use band 3 to target the quasars and look for CO423 emitting galaxies around the quasars. In both cases, we are tracing a similar redshift coverage, around 1,000 kilometers per second from the quasar. But of course, at optical wavelengths, we are tracing a much larger field of view. So I will start showing you the results from the optical observations. We detected 25 Lyman-alpha emitters in all our fields. Here I'm showing some example of our galaxies. And in blank fields over the same volume, we were expecting to detect 18.4 Lyman-alpha emitters. So this is computed from the luminosity function of Lyman-alpha emitters, redshift 4 from Uchi et al. 2008. So this gives us a total overdensity of 1.4 in quasar fields. So on average, quasars trace massive structures at the early universe. Now I would like to highlight that we actually observe a very strong cosmic variant effect. That is what I mentioned before, because 7 of our fields are actually overdense and the other 10 are consistent with blank field. But the overall overdensity is only visible and distinguishable when you stack the information of all our fields. So this is very important to consider. Then here I'm showing the cumulative number of Lyman-alpha emitters as a function of the distance from the quasar. In the red dots is our result, and the line here is the expectation from the black fields, blank fields. So you can see that we are systematically above the blank field, and our overdensity is much more important at small scales and goes reaching the background number density at larger radius. We also measure the quasar Lyman-alpha emitter cross-correlation function, which is this one here. This is a positive quasar Lyman-alpha emitter cross-correlation function. This has a power law shape, which is an indication that Lyman-alpha emitters are concentrated around the quasar. The uncertainties are still large. That is true. But this result is also consistent with the only other quasar Lyman-alpha emitter cross-correlation function measurement at redshift 4 from Fossati et al. 2021. They did a very nice job using Muse. Then they go much deeper, and they constrained it with lower uncertainties. So yeah, our results are in agreement with that. And the other thing that we did was to compute the expectation for the quasar Lyman-alpha emitter cross-correlation function. This expectation is based on assuming a deterministic bias model. So basically you use the information of the clustering of quasars and Lyman-alpha emitters, and you combine this information and compute what is the expected cross-correlation. And this expectation predict 2 times more Lyman-alpha emitter than what we observe in our fields. So we detect a positive correlation function, we detect an overdensity, but we still are missing some Lyman-alpha emitters. Okay, so now I can show you the result based on submillimeter wavelengths. This is our ALMA observations on our 17 quasar fields. We are tracing 6,000 kilometers in total, and we detected 9 emission lines in this area, in this volume. We performed the blind search for emission lines using fine clamps. And if we focus only in the central neighborhood of the quasar, in plus/less 1,000 kilometers per second, we detect 5 lines. And you may be thinking, well, that is not a lot, but this is actually much more than the expectation based on blank field, as I will show you later. Here I'm just showing some example of the detected companions, the images and the spectra. Then, sorry.
5 minutes.
Yes, thank you. Okay, so if I show you the same plot as for the Lyman-alpha emitters, you can see that here the cumulative number of CO emitter is much higher and significantly more higher than the number density of CO emitters expected in blank field in the same volume. In all the volume, we were expecting 0.3 CO emitters, and we are detecting 5. So this is really a lot and result in an overdensity of almost 20. At the same time, we measure the quasar CO cross-correlation function, which is the black point here. The black line is the best fitting. So we detected a very strong cross-correlation function. And we also compare this correlation function with the one that I showed before from Lyman-alpha emitters, which is here. And also with the Lyman break galaxy clustering around the quasar at redshift 4. This is from a previous work in a different quasar sample. So basically, the CO emitters have a clustering very similar to Lyman break galaxies around quasar, but it's much more stronger than Lyman-alpha emitters. We also explore some counterpart of dusty galaxies in our optical images. And here I'm showing the circles, I'm showing the CO emission lines. The squares are the Lyman-alpha emitters, and you can see that only one Lyman-alpha emitter match with a position of a CO line. All the other CO lines seems to be invisible at optical wavelengths, at least for the depth of our optical observations. And even when we relaxed our criteria to select Lyman-alpha emitters, we didn't find any counterpart for those galaxies. So that is very interesting. Now I would like to mention this work. This is from the talk from Romain Meyers yesterday. They show they are targeting 3 redshift 6 quasars observed with Muse and ALMA. So this is the only other work that is tracing both population for high redshift quasar and constraining the clustering of those sources. And as you can see here, they found that the C+ companion, which are the orange point here, are much more strongly clustered than the Lyman-alpha emitters, which are the blue point here. However, both populations are still much more higher than the background number density, which is here shown as this gray and orange area. So this is still a low statistic, but at least is showing that it seems that we are getting better consensus when targeting multiple fields and computing clustering. I have been showing the result from LBGs, LAE, and CO redshift 4, which are also, all of those work claims to be overdense, to find overdensities of galaxies. And also this work targeting C+, redshift 6, having very similar results. So you can check the remind tools from yesterday for more details. Now to start finishing, I would like to mention some possible explanation for this lack of Lyman-alpha emitters and large overdensities of dusty galaxies. So generally speaking, we can say that CO and C+ trace the gas in a galaxy, and Lyman-alpha emission traces instantaneous star formation. So based on that, we could think that a relatively small star formation efficiency in galaxies around quasar could explain the lack of Lyman-alpha emitters in this field. So basically, the galaxies are there, has a lot of gas, but they are not converting that gas into stars. However, we need to be careful because Lyman-alpha emission is a very complex line, and it also traces other properties of the CGM and IGM. So it's not, yeah, thank you. It's not only for star formation. And the other option, which is a very interesting one, is that galaxies around quasar could be more dusty, suppressing or attenuating the Lyman-alpha emission line in those galaxies. So that will explain why we observe much more dusty galaxies and not so many Lyman-alpha emitters. However, this is just a little bit speculative, but we really need a characterization of the properties of the galaxies in dense environment and like trace this in different wavelengths to really understand what is happening there. So to start to wrapping up, I would like just to mention the 4 more important points, in my opinion, that we will be focusing on in the coming future. So the first point is that we need to make continue the work in expanding the blind surveys, making deep and large surveys to constrain better the luminosity function of galaxies at high redshift. This is particularly special at sub-millimeter wavelengths, where we still need more work to do. This is crucial to really characterize the overdensities in quasar environments. The second point is that we need to increase the current statistic of the number count in quasar environment. I hope to have been convinced you that the cross-correlation function is a very powerful technique and is making consensus in this topic. So we really need deep and large surveys of quasars at high redshift. The third one is to trace older galaxy population and characterize the properties of the galaxies in quasar environments. And in that sense, I think that MUSE, ALMA, and JWST will be crucial to really accomplish this goal. And this will also allow us to answer why we are not seeing that many Lyman-alpha emitters as expected. And finally, extend this quasar environment studies at high redshift, but as long as we have the luminosity function well constrained for those sources. So before that, it does make sense to extend this at high redshift. So I think these are the 4 main points in which we should put our attention for making progress on this area. And yeah, finally, I will just would like to leave you with my conclusions. So yeah, thank you for listening.
Thank you very much, Cristina. Great talk. Very, very nice, very interesting. I have a few questions on the Q&A. First, I would like to invite people to ask questions live. If there is anybody who would like to ask a question, please raise your hand. Michael, please go ahead.
Hi, this is Michael Strauss. Great talk. I've also put this question in the chat. When you were talking about the Lyman-alpha emitters at redshift of 4, the filter covers a certain redshift range, and so one has a sensitivity that's a strong function of exactly the redshift, and one has to fold that into the background counts. Can you say a little bit more about how wide that is and how you did that calculation?
Yeah, sure. That is a very important question, actually. Yes, I'm showing this here. The Lyman-alpha meter, the filter is around 3,000 kilometers per second, the full width at maximum. So we are covering around 1,600 kilometers per second from the quasar. And also I would like to mention that the redshift quasar, which is always an issue when redshift comes from optical observation, has been careful checked to have very low uncertainties to avoid being so much offset from the quasar itself. Yes, and we actually confirmed those redshift quasars using our ALMA observation afterwards.
Okay, thank you.
Yeah, sure.
Thank you, Michael. Anybody else would like to ask a live question before we move on to the Q&A? Okay, so I have a few questions here. The next question is by Lisa Young. Have you also investigated the same clustering measurement for the simulated galaxies and QSOs in high Z, so you can characterize any observational selection bias in the clustering measurement?
Yeah, no, actually this work is fully observational. We have not been including simulation here. The only theoretical prediction that we are using here is what I showed here for Lyman-alpha meters, which is telling us that we are detecting less Lyman-alpha meters than what we should detect based on deterministic bias model and dark matter halo physics, but we have not included any other simulation here.
Good. We still have time for questions, so I'm going to continue with the Q&A. So we have another question by Manda Banerjee. How do you rule out other molecular lines at different redshifts rather than CO43 at the redshift of the quasar?
Yeah, that is a very important point, actually, and we were working a lot on that. Maybe I can show you this extra slide that I put here. In our work, we computed the probability that each one of our CO emitters is actually a low redshift contaminant in our survey. And this is what I'm showing in this table. You can focus on the column here. This is the probability that each one of our CO emitters around the quasar used in the clustering measurement is CO120, CO221, and CO322. So you can see that at most that probability is 8%. So we are always having a very low probability to have that one of those sources is actually a low redshift contaminant. This is just based on the luminosity function of those transitions and considering the volume that we are tracing, which is pretty small. So that is why the probability is too small too.
Good. We have a question by Giovanni Mazzolari, yes. Which will be the impact of Euclid in studying quasar overdensities?
Yeah, I think that Euclid will will be great, really great, to increase the number of known quasars at the very high redshift. So that will be very great. But as I mentioned before, we cannot really characterize quasars environment at high redshift if we don't have very well measured the luminosity function of the galaxy population that we need to trace. So as long as we make progress on measuring the luminosity function of the different galaxy population, I think that Euclid will be very useful also for this field, because we also don't have so many quasars so far to study at high redshift, so it's hard to make a very big sample, but for sure would be a very great improvement.
Good. Jorik Mathy asks, among the Lyman-alpha emitters that you do detect, are there any differences between their properties compared to typical Lyman-alpha emitters in blind fields?
Yeah, not really. We have, our Lyman-alpha emitters are detected as in the same way that previous works. And actually, given that we use the luminosity function from Uche et al. 2008, we also compare the properties of our Lyman-alpha emitter with the general population of Lyman-alpha emitter from their paper. And the properties seems to be similar in terms of equivalent width, distribution, etc. So they doesn't seem to be a very special population of Lyman-alpha emitters.
Great, and I think we have 1 more minute, so the last question would be by Masafusa Onoue. Is the host galaxy mass inferred from the clustering of Lyman-alpha emitters and CO emitters consistent with that from QSO clustering of the SDSS observations?
Can you repeat the starting of the question, please?
Yes. Is the host halo mass inferred from the clustering of Lyman-alpha emitters and CO emitters consistent with that from the QSO clustering of the SDSS observations?
Yeah, that is actually, we use that in the other way around. We use the clustering of quasars at redshift 4 to estimate what is the expectation for the cross correlation between quasar and Lyman-alpha emitter. So this is exactly what this line is showing here. So basically we use the clustering of Lyman-alpha emitter and the clustering of quasar at redshift 4. And using this equation here, we combine that information and estimate what is the expectation for the cross correlation. So we are much lower than that expectation. That could be because, for example, for uncertainties in the quasar clustering, that could be, but it's not enough to explain this large difference here. So yeah, we're actually using that in the other way around. We are using the information that we have from quasar clustering.
Thank you very much, Cristina. Great talk and great questions as well. So thank you everyone for asking.
Sure, thank you.
We're gonna move on to our next speaker, Tommaso Zana, who is going to talk about enhanced star formation in redshift 6 quasar companions. Tommaso, go ahead.
Okay. Can you see my screen?
Yes, we do.
Okay, thank you very much. So good morning to everyone, wherever you are, depending on whether you're following this fantastic conference. I am Tommaso Zana, postdoc from Scuola Normale Superiore. And I would like to thank the organizer for letting me share with you what I've been working on in the past few years. So today I will talk about AGN redshift, high redshift AGN, and in particular I will discuss about which is the effect of their feedback on the star formation of the satellites orbiting around the quasars. So I will just briefly introduce the topic, since in the great talk by Cristina, this has been described in details. So high redshift quasars like this one that you can see in this beautiful artistic representation have been found to be very numerous in the universe. A lot of them have been observed till redshift 6 and beyond. And what we think we know about this object is that they likely take their power from the accretion process of gas onto the most massive supermassive black holes. And according to theoretical model of galaxy formation and evolution, we also expect these supermassive black holes to reside within the most massive dark matter halos. But as we have seen, this has not been confirmed yet by observation, because it is really difficult to understand from observation how massive, how dense dark matter halo is. What we can do is just to get an estimate of their mass just by counting how many satellites we can see orbiting around the quasars. And to further complicate this picture, AGNs are able to exchange momentum and energy with their surrounding environment. In this way, they can affect, for instance, the star formation rate of their satellites. They've been proposed, this mechanism has been proposed as able to both quench or trigger maybe the star formation of these satellites, in this way affecting our capability to observe them. And here comes my contribution. I investigated this topic through the use of numerical simulation, which represent one of the best ways to investigate the kind of issue, since in numerical simulation, we have the complete distribution of matter at any time. In particular, I took advantage of a suite of cosmological hydrodynamical simulation, which evolves from redshift 100 to redshift 6, a quite massive halo, dark matter halo of about 4 times 10 to the 12 solar masses, which corresponds to a fluctuation higher than 3-4 sigma than the primordial cosmic density field. Then this is what we would call an overdense environment in the universe. Here you can see the evolution of the gas density map from redshift 10 to redshift 6. And in particular, I analyzed 2 simulations in this suite with the same initial conditions and same subgrid physics, but with the only difference for the prescription for black holes. One simulation, dubbed AGN Cone, has a prescription in order to see the supermassive black holes at the center of the most massive dark matter halos. And also there is a prescription in order to make them eject powerful outflows in a bicone of 45 degrees of aperture. The other simulation that I analyzed is just a control run with no prescription for the black holes, so no black holes there. What I did was to identify the population of satellites in both the simulations. Here you can see a snapshot in these 2 simulations. This is the stellar density maps. Here you can see as an example 6 galaxies that I matched in the 2 simulations. And then I developed a semi-analytical model based only on momentum conservation in order to compute which is the cumulative energy hitting, for instance, on a target galaxy that you can see here from the whole network of accreting AGNs. So I'm not going into the detail of this model for time reasons. And here I'm going to show you the results. These are 3 galaxies that I selected, 3 galaxies out of the 6 that I showed you before, 3 galaxies that I think they better exemplify what is happening here. Here you can see the evolution of this cumulative energy as it is being computed in the previous mode with my toy model. The dashed lines has the only purpose to show which galaxies has been strongly affected by the AGN, like the first 2, and the last one is the least affected in these 3. And I want to compare the evolution of this cumulative energy with one of the most important properties thanks in galaxy evolution, which is the star formation rate here. Red lines are for the simulation with the AGN, blue line without it. And in the middle line, you can see the relative difference in order to better understand what's going on. So as you can see, it seems that the higher is the energy hitting on the galaxy, the higher is the difference in the star formation rate. The timing is also remarkable, and maybe you can see also the last galaxy, which is the least affected, shows the least difference in the star formation rate, and everything seems to be concentrated at the very last moment of the galaxy evolutionary history. So one may wonder if this effect of enhancement can be seen, if this can affect our capability to observe the satellites. And I quantify this by computing the C+ luminosity of this satellite population. This is basically how many satellites you would observe with this sensitivity. Again, red lines for the simulation with the black hole, blue line the other. Shaded area are the Poissonian noise. And I decided to compare this with the result from one of the most recent survey in C+ satellites from Venemans et al., where 27 quasars has been observed and the satellites have been detected. Here you can see the average number of satellites in this survey around a single quasar. And as you can see, they are well within the error for our 2 simulation, meaning that this observation actually agree with what we simulated. So an overdense region. But interestingly, when we consider only the 4 more massive, more luminous far infrared quasars, the average number of satellites increase. And when we consider the most luminous quasar in far infrared, we also need the AGN feedback in order to explain this observed number of satellites, which is very interesting. I know that for time I will have to leave my conclusions here, and I would like just to highlight this. So first of all, we not only can blame the feedback according to our results in order to explain why sometimes we cannot observe satellites, but satellites can also, feedback can also increase the star formation when outlaws, for instance, directly hit these galaxies. And also recent C+ observation agree with this overdense scenario. And in some cases, feedback can also be seen as instrumental in order to explain some overdensity. So thank you very much for the attention. I will stop here.
Very nice talk, Tommaso. Perfect timing. Thank you very much.
Thanks.
Perfect. So yes, very good. So anybody would like to ask a sort of live question? If not, oh yes, we have one. Yes, Melanie, go ahead. Go ahead, Melanie.
Oh, sorry. Do you hear me?
Yeah, now we hear you.
Oh, sorry. Yeah, sorry. I screwed up.
Yeah,
I was saying a nice talk and nice results. I was wondering if any of your results would change with super Eddington accretion instead of a normal accretion. That's a tough question, I know.
No, that's a great question, actually. So I think that this strongly depends on, okay, that can be a factor, a very important factor, but there are a lot other factors that are as important as that. So it is possible that if galaxies are undermassive and maybe very near to the ejection of the material, their environment can be stripped by the quasar feedback. And for it, otherwise, maybe galaxies that are massive enough to retain their gas content, they can also get more gas, and then for that reason they can increase their star formation rate. For instance, this is a very important factor. If we have super Eddington accretion removed, then we are not capping the accretion process of quasars, then we would increase in some cases this the ejection of the outflows, and in this case we just I think we would have a more diverse cases. So some galaxies would be disrupted, and some galaxy maybe would get even more fuel to form more stars.
Okay, thanks.
Thank you very much. Yes, so I think we don't have time for more questions, so we're going to move on to the next talk with, go here. So it's Fabrizio Arrigoni, who's going to talk about a look at the halo and large-scale environment of high-Z quasars with a known extended Lyman-alpha mission.
Okay, thanks. Can you see my slides?
Yes, we can.
Okay, perfect. So thanks. I'm Fabrizio Arrigoni Battaglia, in short Fab, and today I will give you a very brief update on what I've been working with my collaborators in trying to understand why we see so diverse Lyman-alpha nebulae around high redshift quasars. So let me start with reminding you that nowadays we can target quasar from the ground, from redshift 2 up to the highest redshift in Lyman-alpha, and we can detect extended glow in Lyman-alpha around these quasars. And here I just show some examples from redshift 2, redshift 3, and out to redshift 6. For redshift 6 quasar, we will hear a talk tomorrow by Tiago Costa. And what I like to stress is that not only we can look at the surface brightness in Lyman-alpha around this quasar, but also at the kinematics, thanks to the IFU instruments that nowadays are available. And one nice properties of these quasars, of this quasar nebula, is that they seem not to depend on the luminosity of the central quasar. So here I show you how diverse can be a Lyman-alpha nebula with a quasar at roughly the same luminosity. So you can see that we go from very small, almost inexistent Lyman-alpha nebula out to extreme nebulae where the surface brightness is above 10 to the minus 17 for hundreds of kiloparsec. And I've started to look in why this is the case, and we took a sample of quasars with Apex. We targeted the molecular line tracers, and what we found is that the small Lyman-alpha nebula around quasars seems to be associated with the most massive molecular reservoirs. And so most likely what we are seeing here is the obscuration from the host galaxy that is playing a role in shaping what we can see on large scales. So basically, ionizing and Lyman-alpha photons produced by the quasar are not able to escape out to CGM scales in these sources. On the other hand, if we focus on the very large extended nebulae, what we find is that only 4% of the so far targeted quasars, these are about 200 of quasars, only show this nebulae in about 4%, okay? And this number is put this object into being very rare systems, like with densities like the also known Lyman-alpha blobs. These systems also have multiple agent systems, pairs, triple quasars, or quadruple quasar system. To try to understand the properties of these extreme outliers of the quasar population, we started a multi-wavelength effort called AMUSE2, which stands for a multi-wavelength study of ELAN environments, and basically with the aim of constraining the properties of the objects embedded in this ELAN, constrain different gas phases on these large-scale structures, and constrain the environments from the halo out to large scales. And we have been using several facilities. Here I just show the facilities in the optical and in some millimeter bands that I will touch upon very briefly next. So we have about 3 papers at the moment. I put them here on top, and we'll go through their main results in the next few minutes. So the first paper is about the so-called fabulous ELAN at redshift 3. This object has a free AGN within a few tens of kpc, and within our multi-wavelength dataset, we have also ALMA observations targeting the CO524 line, and we detect the free AGNs here, the top 3 sources, and also what we have labeled LAE1. And as you can see, these sources have quite broad lines, which can be already a trace of the fact that they live in a protocluster region. We also using a CD fitting, we constrain several properties of these objects and infer the Nelo mass. Okay, infer the Nelo mass for this system to be of the order of 10 to the 13 solar masses. The CO524 emission is resolved spatially, and we can tentatively place the spin of these objects and look and compare it to the large-scale structure, here in blue, the Lyman-alpha emission. And what we found is that the spin of the objects is almost aligned to the direction to the quasar. So basically, this seems to be in agreement with expectation from simulations that place the spin of a low-mass system aligned to the large-scale structure they're coming from. We also attempt a first estimate of the baryonic components within the halo. And what we found is that the warm hot component that we cannot observe but only infer should be dominant in this system. The second paper of the series focus instead on trying to characterize the large-scale megaparsec environment of 4 of these ELAN systems, and we took some millimeter maps spanning a range that is basically the area expected for a protocluster at this redshift, and we found overdensities of 850 macron sources, basically in excess of counts of a factor of about 3.6 in each field. And if we assume that all these sources are associated with the central ELAN, then we find that the star formation rate density in these systems is similar to protocluster at similar redshift, and of about 300 times the cosmic mean. The third paper targeted the so-called slug ELAN. This object is at redshift 2, is about 500 kiloparsec wide, and is known to be sitting in a quasar pair. What we discover here with ALMA, thanks to the 2 millimeter continuum and CO423 C1120 emission, is that within this nebula there is an embedded dusty star-forming galaxy, and you can see it here. And using also the other, using also the other observation of the other ELAN, we found that the gas fraction and the gas-to-dust ratio of the objects within ELAN environments are at the low end of the submillimeter and quasar population at similar redshifts, meaning that this environment seems to be harsh on their galaxies. We find also the first evidence of gas stripping of a DSFG at redshift 2 due to the halo, hot halo of a host quasar. I conclude here, and I hope I motivated you to go and check out these 3 papers. Stay tuned about upcoming results. Thanks.
Thank you very much, Fabrizio. Very nice talk. We have time for a very quick question with a short answer. Anybody? Okay, I think we can, well, thank you very much again to our speaker. I think we can move on to the next presentation just to catch up a little bit so we are keep the time correct. Our next speaker is Weida Hu, and we'll hear about a Lyman-alpha protocluster at redshift 7.
Hi, can you see my screen?
Yes, we do see your screen. Yes.
Thank you. So, hello everyone. I'm Weida Hu from University of Science and Technology of China. I'm now a postdoc working with Junxian Wang. I would like to thank the organizer for this opportunity to present our work here. The title of my talk is the Lyman-alpha protocluster redshift 7. Here list my collaborators. First, I would like to introduce Lyman-alpha galaxies in the epoch of realization survey. Larger survey is a narrowband survey to search for Lyman-alpha emitters at redshift 7. We designed a narrowband filter to with central wavelengths of 9,642 angstrom and the full width at half maximum of 19.2 angstrom. So we can use this filter to select Lyman-alpha emitters in the redshift range of 6.89 to 6.97. The filter was installed on the dark range camera on the Blanco 4-meter telescope. The dark range camera has a very large field of view and a red sensitive camera. Its total response at 9,600 angstrom still larger than 50%. This combination makes larger is one of the most efficient survey in searching for Lyman-alpha emitters in the epoch of realization. So we aim to construct a uniformly selected Lyman-alpha emitter sample at redshift 7. We expect to select more than 600 Lyman-alpha emitters, and the area coverage of the larger survey is more than 20 square degrees. We'll adopt a wedding cake survey strategy to discover both bright and faint Lyman-alpha emitters. I want to highlight that the larger survey is one of the most is the largest survey at the redshift 7. The survey volume is comparable. It can be directly comparable to the cosmological simulations. Based on this Lyman-alpha emitter sample, we can study both the galaxy property in the early universe and the history of the realization. Up to now, we have observed 4 fields, including cosmos, change-relative field south, gamma, and wide field. We have selected more than 160 Lyman-alpha emitters at redshift 7 in these 4 fields, and we constrained the neutral hydrogen fraction at redshift 7 is less than 0.33. In my 2019 paper, we identified a very special region in the cosmos field. We obtained 47 of narrowband exposure and selected 69 Lyman-alpha emitters in the cosmos field. This plot shows the spatial distribution of Lyman-alpha emitters candidates in this field, and the contour shows the galaxy number density. You can see a highly overdense region consists of 14 Lyman-alpha emitters and with overdensity of 5.1. This region contains 4 numerous Lyman-alpha emitters, while there are only 8 in the whole cosmos field. Its high overdensity tells us it's a protocluster at redshift 7. We use several methods to find as much number of Lyman-alpha emitters in this protocluster as we can. Finally, we find 21 member Lyman-alpha emitters in this protocluster, and 60 have been spectroscopically confirmed with Magellan, MX, and LDSS. Here are the example of the of the spectra, you can find they have clearly asymmetric emission line, indicating they are Lyman-alpha emitters. The volume of this protocluster is 66 times 30 times 26, and the local density is 5.1. It will collapse into a massive cluster at redshift 2. So if we assume all the matter within this protocluster will collapse, its mass will be 3.7 times 10 to 50 solar masses. During the epoch of realization, the hard UV photon escaped from the galaxy to analyze its surrounding neutral hydrogen and generate a ionized bubble as indicated by this figure. The ionized bubble could gradually grow and merge with adjacent bubbles into a very large ionized bubble. And until the IgM is fully ionized, the protocluster in the epoch of realization may need the production of such bubbles because they have high number density of galaxies and they may have positive effect on the star formation inside those galaxies. So we calculated the bubble size of the member galaxies in the epoch in the protocluster based on a relation between the bubble size and the Lyman-alpha luminosity derived by a simulation work. The red figure shows the red figure shows the bubbles of spectroscopy conformations. The summed volume of the ionized bubble of all 21 Lyman-alpha emitters is 6.6 times 10 to 5. The total ionized volume is even larger than the volume of the protocluster. This means that the individual bubbles of this protocluster, of the galaxies in this protocluster has overlapped. The bubbles are in the act of merging with adjacent bubbles into one or two giant bubbles. In other words, the intergalactic medium within this protocluster is almost fully ionized. However, how the ionizing photon escapes from the galaxy and how many ionizing photons can the galaxy produce are not well understood. So we submitted a proposal to James Webb Space Telescope to observe oxygen 2, oxygen 3, H alpha, and H beta emission lines of the member galaxies in its substructure, and we were awarded 35 hours. We are going to start in their interstellar medium properties, ionization parameters, and etc. Here is a summary of my talk. We found a protocluster redshift 7 consists of 21 Lyman-alpha emitters, most of which have been spectroscopically confirmed, and this is the most distant protocluster that has already been spectroscopically confirmed. This protocluster will collapse into a cluster with mass of 3.7 times 10 to 15 solar masses. We also found the intergalactic medium within this protocluster have been fully ionized. Thank you for listening, and I'm going to stop here and take questions.
Thank you very much, Weida. Almost perfect timing. We have time for at least one question. Lisa Yoon asks, can you tell what the source of powering Lyman and alpha emitters is, star formation or gas cooling?
Thank you, Yo-san. This is a good question. So the power of Lyman-alpha emission is star formation. And for the second question, in narrowband images, all of these galaxies are compact.
Good. I think we have time for a very, very short question and answer. Here we have, what are the, also Lisa and Ewan asks, I think, let me see. He asked, what are their Lyman-alpha morphology in general, extended or compact?
Yeah, compact. We can see the Lyman-alpha emission in the narrowband images.
Very compact. Good. Thank you very much. So we're just in time here. So we're going to move on to our next speaker. Is the last talk of this session before the break. So we have here a talk by Yetli Rosas Guevara, who will talk to us about the properties of void galaxies and their black holes in the Eagle simulations. Yetli, the floor is yours.
And hello.
Hello. We see you and we hear you.
Can you see my screen now?
Yes, we can.
Okay, thank you. So I'm Yetli Rosas Guevara, and today I'm going to talk about the properties of void galaxies and their black holes in the Eagle simulation. This work has been in collaboration with Patricia Tisera, Enrique Pailas, Nelson Padilla, and Claudia Lagos. Let me start with a brief introduction. Now it is well known that the largest scale structure can be described as a cosmic web with thin filaments, clusters, and surrounded by under-dense regions. These under-dense regions occupies more than a half of the volume of the universe. And this is the environment, the large scale environment that I will focus today. And it's called cosmic voids. What we know so far about the role of the environment in galaxy evolution and their black holes is that void galaxies have lower stellar masses, are bluer, and with late type morphology. Other properties, such as star formation rates and metallicity, are still in debate, but well, there are some differences in the galaxy population. But if the galaxy properties are influenced by the large scale environment, well, we expect that also the black holes could be influenced by the large scale environment as well. And there is some evidence that there is a higher AGN activity for especially bright AGNs and for in massive galaxies, but also the fraction of galaxies with moderate luminous AGNs is similar in different environments, so still is in debate as well. The outline of my talk is that I will focus on 5 findings that I have in my work. And this was using the Eagle project, which is a suite of hydrodynamical cosmological simulations with modules of subgrid physics of galaxy formation. These modules has been calibrated to match the low properties, the low redshift observables of the galaxy population. And I will focus on the largest simulation that is that has a volume of 100 megaparsec cube and go from redshift 127 to redshift 0. Also, I will use the void catalog from Pailas, which identifies sphericals under density in a galaxy distribution and characterize each of these voids with a center and the size of the void. This catalog of voids consists of more than 700 voids with sizes between 3 and 25 megaparsecs. We also focus on the central galaxies with the stellar masses larger than 10 to 9 solar masses, and results in more than 7,000 galaxies. We divided our catalog of galaxies in 4 regions according to the distance to the closest void. But here I only focus on the inner void galaxies, which are in the inner parts of the void, and in the skeleton galaxies that are very far from the void. And also these regions will have the same stellar mass distribution than the inner void galaxies. So I will present my results, and the first finding that I have is the galaxies in voids are more star forming. Here I present the galaxy of quenched galaxy, the fraction of quenched galaxies as a function of the stellar mass. So you can see the inner voids as a blue line and a skeleton as a red line, that the inner voids present less quenched fraction of galaxies in comparison with the skeleton galaxies. And this happened on all the stellar masses that we analyze, except for 10 to 10 solar masses. The second finding is that low mass galaxies in voids are less metal rich than denser galaxies. So here in the left panel, I show the average star forming gas phase metallicity stellar mass relation. And as a blue line is the inner void galaxies. And we can see that they present lower gas phases metallicities in voids than in a skeleton. We also explore the cumulative distribution of star-forming gas phase metallicity gradients, and we see that negative metallicity gradients are more common in voids than in skeletons. And when we look at the galaxies with AGN feedback, here I show the fraction of AGNs, the fraction of galaxies with AGN activity. We see that this AGN activity is higher in inner voids, and when you go to denser environment, well, this decreases or is almost flat as is more dense the environment. With Eagle, we have the advantage that we can explore the histories, the assembly histories of the galaxies and the black holes. And here I present the stack mass weighted edge distribution of the stellar populations for different stellar mass. And we don't find any difference between inner voids and skeleton galaxies, as you can see in the age of the stellar populations, except for the massive galaxies that are formed earlier in voids. And the last finding is that I have is that how is the growth of the black holes in voids in comparison with the skeleton. Here I present how is the mass of the black hole respect to the final mass of the black hole, and we can see that the black holes in inner voids form later in time than the skeleton than a skeleton galaxies, that the black holes that are residing in more skeleton galaxies. This is the outline of my talk. As I said before, I focus on the 5 findings that I have so far, and that's it.
Very nice talk, Yetli. Perfect timing. Thank you very much. So we have a couple questions here in the Q&A. Anybody would like to ask the question live? Michael, for example, yes, or Melanie? Yeah, let's go for, I have Melanie here first. Go ahead, Melanie.
Hey, hi. I'm happy to see that people start investigating galaxy on AGN in cosmic void. I was wondering if you had a chance to compare with our results from 2 years ago. We have a paper with Horizon AGN
Yes.
where we were finding a lot of AGN in void, and this is, I think, exciting because, as you say, black holes may form later on in void. So I think the fact that they are AGN, we can actually detect them. So yeah.
Yeah, I didn't mention, but yeah, we compare with your work that you have in Cosmic Voids with the Horizon AGN simulation, and yeah, we have similar results in the sense that the AGN activity is higher in these under these regions.
Thank you.
Thank you very much. We have one more question by Michael. Please go ahead.
Hi, thank you for a very interesting talk. It looks like Darren Croughton has asked the same question that I have, which is what triggers the AGN that are found in voids? Do they often have close companions that cause the AGN to be fed? Do you have any insight on that?
I think, yeah, this is a good question. I explored the major histories of the galaxies to see if, for example, in the voids have a recent merger, but I didn't see any difference in the merger histories of the galaxies, except that, for example, in skeleton galaxies, they can have the last merger in different times of the simulation. But for the inner voids, they have a very narrow time where they have the last major, for example, that is 7 gigayears. I didn't put here my results because there are a lot. And the other thing that is happening is that, yeah, the AGN, also I didn't show the mass black hole stellar mass relation, but we found that the black hole mass stellar mass relation for the most massive galaxies are under massive in inner voids. So they didn't get enough mass to grow, whereas in the intermediate masses, you see that they are a bit overmassive, the black holes. And I think this, for that reason, they overmassive black holes. So I think for that reason, they are still being active, perhaps. Being active, the most massive galaxies, because they still have not reached the relation between the black hole mass and stellar mass relation. When it's supposed, at least in simulations, when it's supposed, the AGN feedback start to be efficient to regulate the star formation.
Okay.
Sorry, I have the results, but there is not the result. I don't know if it's clear.
Yes, thank you.
Thank you very much again, Yetli. Very nice presentation. Great questions too. So I think this talk concludes this first session of today. We thank again all the speakers and everyone here. I think it was a very, very nice session. So we're gonna have a break, and after the break, we resume the meeting at 10:40 EST. Which will be 12:40 here in Chile. So there are some questions that have not been answered. So I believe they will be put on Slack so you can continue the discussion there. Thank you very much.